For centuries, man has struggled to impose order on a perversely irregular world, and what he couldn't understand was often ignored. Now, armed with a new weapon, the computer, man is at last challenging the kingdom of chaos, describing the shapes and forms of a world where the only straight lines are the ones he has introduced. A new science is emerging from this challenge, a science which promises to describe and explain the infinite complexity of the busy world in which we live. It's a science which is producing a new geometry that offers an insight into the surprising paradox that there is order, even within discord. It's a science which is turning conventional thinking on its head. A science called chaos. That weather is one of the more unpredictable features of our daily life. For 100 years, scientists have struggled to find the rules that govern our weather, hoping that this would enable them to produce accurate long-range forecasts. We now know that they struggled in vain, that even with today's technology, the task is simply too hard. The European Centre for Medium-Range Weather Forecasts is the most advanced meteorological centre in the world. Here they try to make sense of the diversity of our weather. Every day, 100 million measurements gathered from around the world are fed into an enormous computer model of the Earth's atmosphere.
What we do is divide the atmosphere up into segments that are about 100 kilometers by 100 kilometers in the horizontal and about 1 kilometer in the vertical. And it takes about 1 million of these segments to represent the whole atmosphere. And every day we run the model to produce a weather forecast for 10 days into the future. Now on the present machine, which is essentially one of the most powerful computers in the world, this takes about 3 hours, just under 3 hours of computing time to produce a 10-day forecast. Now to give you some idea of the complexity that's involved with all these interactions going on, every second of that 3-hour integration period, the computer performs about 400 million calculations.
As recently as 20 years ago, this ability to compute 400 million calculations per second was simply inconceivable. Indeed, in 1959, meteorologist Edward Lorentz was more than satisfied with the 17 calculations per second that his brand new computer could perform. With it, he made the discovery that gave birth to a new science.
The computer that we did our original work on, this Lyle McBee LGP30, here with a console and the working portion here. This was a medium-speed computer in its day. We first got a hold of it in 1959. It sounds rather crude by modern standards because the computer took 10 whole seconds to print out just one line of data. We had condensed the numbers so it printed things out to 3 significant places, although they were carried in the computer to 6, but we didn't think we cared about the last places at all. So I simply typed in what the computer printed out one time and decided to have it printed out in more detail, that is, more frequently. And I let the thing run while I went out for coffee, and a couple of hours later, when it had simulated a couple of months of data, I came back and found it was doing something quite different from what it had done before. It became obvious that what happened was that I hadn't started with the same conditions. I started with round-off conditions, so that I started with the original conditions plus extremely small errors, but in the course of a couple of simulated months, these errors had grown. They doubled about every 4 days. That meant in 2 months they'd doubled 15 times, or a factor of 30,000 or so, and the two solutions were doing something entirely different. And I have some of the original output here from the computer. What I've did was to print symbols and then go over it in blue pencil all to illustrate it, and this is one of the graphs that I obtained. If you look at a fair stretch of this, you see that there are certain typical things that this particular system of equations does. It has rather pointed minima, rather extended maxima with little waves in them, but it doesn't do exactly the same thing twice. It does one thing, then it does something like it, but something that isn't quite the same. It's a bit different.
The desktop weather from this second, slightly modified computer run appeared tantalizingly familiar. Lorenz studied the new data, looking for regions where the output appeared to match the first run. And yet, although many of the peaks and troughs looked similar to the first printout, when he tried to match them up, the patterns soon drifted apart. Lorenz's computer had a message for him, and science.
What Lorenz's work tells us is that no matter how complex our models become, and no matter how good the initial data becomes, there will be a limit beyond which we cannot provide accurate forecasts of the instantaneous weather.
The discovery has since become known as the butterfly effect, because in theory, even the tiny disturbance in the air caused by a single butterfly in flight can tip the balance of our weather and create a chain reaction straddling time and distance, ultimately altering the course of a tornado on the other side of the world. It's an effect which has upset quite a few scientific apple carts, since it means that even the tiniest errors of measurement make accurate prediction impossible in many, if not all, physical systems. Until quite recently, we explained the world using the rigid geometry of the Greeks. We lived, it seemed, in a clockwork universe, governed by immutable laws. They were the laws of motion, first identified by Sir Isaac Newton in the 17th century. Initially, he described how gravity rules the motion of the planets. Subsequently, it was believed that all physical systems obeyed these laws, and that the key to accurate prediction was simply accurate measurement. In fact, this new natural philosophy seemed to lead inevitably to a conclusion, first proposed by French mathematician Pierre-Simon Laplace, that if you could exactly measure the position and motion of every point in the universe, predicting the rest of eternity would be simply a matter of doing the sums. Towards the end of the last century, Laplace's compatriot, Henri Poincaré, began to realize that if the universe were driven by clockwork, then it ticked in a complex and even unpredictable way. Applying a new geometry to Newton's laws of motion, he tried to reach a deeper understanding of the dynamics of nature. But time and again, he came to the edge of a mathematical abyss, face to face with unpredictability and chaos. What had happened? Was Newton wrong?
Clearly, Newton was right. We've been using Newton for 300 years to predict the motion of heavenly bodies, to predict the motion of spaceships, etc. On the other hand, when you try to fine-tune Newton, what you find is something that's a little bit different. Newton says that, yes, if we know the initial behavior, the initial conditions perfectly, then we can predict what will happen. The unfortunate problem there is the if. We don't know anything perfectly in nature. It's impossible to pin down precisely to 15, 30, 50 million decimal places the position of a particle in space. Let me show you what this little machine does. What we basically have is a little metal ball, and underneath this plate are a bunch of magnets. So this little ball can be attracted to various of these magnets. Now, it's a very simple physical problem to take the ball and let it go and ask what happens. That's a motion that should be described by Newtonian physics, yet here's something that behaves totally chaotically. Watch how the ball goes. It bounces back and forth from side to side in a very irregular pattern. Let me try to start the ball exactly where I started it before, right about there. If I start the ball from essentially the same position, you'll notice that after a very short time, the ball starts to behave in a completely different manner.
It's the butterfly effect again, in an inherently unpredictable system. In a predictable system, such as when a ball drops onto a flat surface, the behavior of one ball closely matches the behavior of others dropped from the same height. There will be small discrepancies, but plotting the path of the first ball allows you to approximately predict the paths future balls will take, and be right. Bouncing a ball off some round white pegs changes everything. Now, knowing the path of one ball will not help you to predict what the paths of others would be. This is the butterfly effect again. Tiny variations in the paths of the balls are being amplified on every bounce, making prediction impossible.